We're now going to look at segment lengths within a circle instead of looking at those angle measures. When we have our segment lengths, we're talking about the segments that are formed from those different types of intersections that we looked at for our angles. So we have those interior intersections and we have our exterior intersections. We have three different types of intersections that we're looking at, and each have their own specific way of us finding different side measures. So when we're looking at an intersecting chord or secant inside the circle, we are going to use this relationship. So A times B is equal to C times D. So you can sort of think of the 2 halves multiplied is equal to the second 2 halves multiplied. For type 2, we're looking at intersecting secants outside the circle. So we have this extended piece outside our circle. When we do this relationship, we're looking at A times the quantity A plus B, so the small piece times the entire length, is equal to C times the quantity C plus D. So again, the small piece to the entire length. Our third type is intersecting secant and tangent outside the circle. When we do that, the relationship is squaring A. So A squared is equal to B times the quantity B plus C. So the small piece times the entire thing. We're going to use those different relationships to solve these next couple of problems. So for number 1, when we solve for x, we're going to first find the type. This is an example of type 1. So we have the intersecting chords inside our circle. When we set up our relationship, we're using this as our guideline. So it's going to be 14 times 15 is equal to 10 times x. And then when we solve for x, we find that x is 21. Number 2 is that same type, so intersecting inside our circle. This time they gave us one of our pieces was an algebraic expression, 5x minus 1. So setting up that equation is going to look like 6 times 6 is equal to 4 times the quantity 5x minus 1. So just multiplying those 2 halves together. When we do that, we find that x equals 2. For this problem, it did ask us to find the length of BD. So in order to do that, we're taking x equals 2 and plugging it in. When we plug it in, we find that 5 times 2 is 10, 10 minus 1 is 9, and then we have to add the top piece of 4 to get that BD is 13. Number 3, we're also intersecting inside our circle, so we're multiplying those two pieces together. When we multiply our two pieces, we get 27 times x plus 5 is equal to 24 times x plus 7. And for this problem, we just need to solve for x, and x equals 11. Number 4, we're finding TQ, so just a piece of that line. In order to find TQ, we're going to set up our intersection problem. We have 18 times 2x minus 5 is equal to 14 times 2x plus 1. We're going to solve and we find that x equals 13. And then to answer the question, we're going to plug 13 back into the expression 2x plus 1 to find that TQ is 27. Number 5 is an example where the intersection is outside our circle, so it's two secants that we're looking at. For this, the way we set up our equation is going to be 9 times the quantity of 9 plus x, so the small piece and then the whole thing, is equal to 8, the small piece, and then the quantity of the entire thing. They got 27 by just adding 8 and 19 together. If you need to write it out first as 8 plus 19 and then add it together, that's perfectly fine. When we solve for x, we find that x equals 15. Number 6, we're finding NL, so that entire length. Before we can find NL, we do need to find what x is. So x is the length of NM. When we set up our equation, we get 13 times the quantity x plus 13, so we're adding the two pieces together, is equal to 10 times 52. Again, adding 42 and 10 together. When we solve for x, we find that x is 27. And then we're going to add 27 and 13 together to find the length of NL to be 40. Looking now at number 7. So number 7, we are looking at two intersecting secants outside the circle. When we set up our problem, we are going to do 8 times 3x plus 12. The way we get 12 is by adding 8 and 4 together, so just combining like terms. If you would like to rewrite it as 3x plus 4 plus 8 first, that's perfectly fine. On the other side, we have 7 times the quantity of 5x plus 9. Again, 7 plus 2 is how we get 9, but we can rewrite that out as 5x plus 2 plus 7 if that helps. When we solve for x, we find that x equals 3. Number 8, we're also looking at those intersections outside of our circle with our two secants. So setting up this problem, we are going to have 12 times x plus 20. So the little piece times the entire thing, 8 plus 12 is how we got that 20, is equal to 15, and then times the quantity, x plus 14, so 15 minus 1 is 14. When we solve, we get that x equals 10. And then for this one, if we want to find yz, 10 minus 1 would be 9. So our final answer for number 8 should be 9. Number 9 is that third type of problem. So that third type of problem is when I'm taking the 24, I'm going to square that, and then I'm going to set it equal to 18 times the quantity of the entire thing, so 18 plus x. When we solve for x, we find that x equals 14. Number 10, we're finding the length of Pn. Pn, we are going to be using that 5x minus 1, so once we find x, we'll plug it back in. Our equation is taking that 16 and squaring it on one side of our equation. On the other side, we're doing 8 times the quantity of the entire thing. So 5x minus 1 plus 8, or we can write it as 5x plus 7. When I find x, I get that x equals 5. And then I'm going to plug 5 back into our expression of 5x minus 1 and find that Pn equals 24. A couple more examples to look at. For number 11, we're finding x. When we write our equation, we're going to get that x squared equals 27 times 48. 48 is getting 27 plus 21. When we solve for x squared, we find that x equals 36. Remember, to undo a square, we just take the square root of both sides. Number 12, we have that exterior intersection where we're going to have to square 3x. When we square 3x, it's important to write it as 3x in parentheses and then the square, because we need to square both things. And then on the other side, we have 9 times 25. 25 is 16 plus 9. When we find x, we get that x equals 5. Our next couple of examples are going to be using factoring. So when we look at number 13, we're first going to start with setting up our problem. Remember, if we're intersecting inside that circle, we're taking the two parts and multiplying them together. So that's going to be x minus 1 times x plus 6 is equal to 12 times 10. When we do this, on the left side, we are going to have to distribute and find that x squared plus 5x minus 6 equals 120. We have to get one side equal to 0 before we can solve, so we have to subtract 120 over, and then from there, we're going to factor out the left side. Once we factor out our left side, if it's still equal to 0, we're going to set each part equal to 0. So x plus 14 equal to 0, and that gives us x equals negative 14, and x minus 9 equals 0, and we're going to find that x equals 9. A length can't equal a negative number, So that's why we are using x equals 9 for this problem. So a little bit more work with our algebra, but setting up that problem is still the same way as before. Number 14, we have those two secants intersecting outside our circle. When we write that out, it's going to look like x times x plus 5 on one side and 4 times 6 on the other. We'll distribute that x on the left side. Again, one side has to be equal to 0, so we have to subtract that 24 over. We're going to factor out the left side and set each piece equal to 0. When we do that, we get x equals 8 and x equals negative 8 and x equals 3. We can't have negative 8 as a length, so that's why we're using x equals 3. Number 15, we have those intersections outside the circle with two secants. When we write out this problem, we are going to write it as x times x plus 15 equals 5.5 times 28. 28 is 22.5 plus 5.5. Same thing as before, we're going to distribute first and get everything on one side, so 0 is on the other. Once we have one side equaling 0, we can factor. When we factor, we're setting each piece equal to 0 to solve for x. We get that x equals negative 22 and x equals 7, and x equals 7 is the only logical choice. Last example for our segment lengths is number 16. Number 16, we do have the intersection outside, and it's that third type, so we are going to take the x plus 5, and we're going to need to square that, and that's equal to 12 times 27. When I have x plus 5 squared, remember that's x plus 5 times x plus 5. So when I FOIL that out, I get x squared plus 10x plus 25. We need to make one side equal to 0, and once that happens, we can factor the left, setting each piece equal to 0 and solving. We find that x equals 13 since we cannot have a negative length. So when we're looking at those segment lengths in a circle, we really need to make sure that we remember our different relationships with those sides. And if we do that, we'll be able to find any segment length within a circle.